Hello, everybody. Today we're going to be talking about orbitals. So, what even is an orbital? If you remember, an orbital is basically a probability distribution of where the electron is. And an orbital is our atom, right? It's a 3D model of our atom. And we have these electrons in our atoms, and they're all moving around randomly. And so it's a 3D probability distribution for an electron of where you would find it 90% of the time, because they're constantly moving around. And so this is basically what it's going to look like, the electron cloud version of it, instead of the old version of the loops and orbiting per se. But it's also a probability distribution of the wave function. So let's talk about energy levels. What is our N number? That is going to be our energy level, or how big the atom is, our quantum number N. So the higher the N number, the higher the energy level, obviously. And we have these different energy levels. And you can see that these little rings can make the atom bigger or smaller. And so as N increases, the distance increases from the nucleus also increases. And this distance creates a larger energy level, which makes sense because as you have a larger atom, that requires more energy to keep it in one atom, because the larger atom you get, the more unstable it is, because it wants to combine with other atoms. And so that's why it requires more energy to have a higher energy level, if that makes sense. And going back and forth between those levels. So what is our second quantum number? If you remember what the second quantum number is, this quantum number is L, and it describes the shape of our orbital, also known as angular momentum number. This angular momentum number can range from 0 to L minus 1. So this also tells us how many orbitals are in this place. So what is going to be this orange orbital? Is that going to be, what letter is that going to be? It's going to be an S orbital. And this middle one is going to be a p orbital. And the clover leaf is going to be a d orbital. We also have f orbitals, but those ones are a little weird and funky. But each of these s, p, d, and f, they have a code per se, or a number that corresponds to the letter that helps us differentiate, oh, if I tell you this number, then it's an s orbital. So there's our f orbital. Our L is going to equal 0 for the s orbital, and L equals 1 for the p orbital, L equals 2 for the d orbital, and then L equals 3 for the f orbital. So these range from 0 to L minus 1. And that's going to be our angular momentum number. So if we want to list those out, how that relate to N number. So if we have energy level 1, that's only going to have an s orbital. It's only going to have L equals 1. Because L minus 1, there's just 1. So for N equals 2, we have L equals 0 and 1. So N is almost like the number of L numbers that we'll have, or the number of just the corresponding shape that it will be. So for N equals 1, there will be an s orbital. For N equals 2, there will be s and p orbitals. So these numbers of 0 and 1 are just corresponding codes to the s, p, d, and the letters themselves tell you what shape they are. So for n equals 3, we'll have L equals 0, 1, and 2. And those are the corresponding s, p, and d orbitals. And then for n equals 4, we've got L equals 0, 1, 2, 3, and then s, p, d, and f orbitals. See, this is what the f orbitals look like. They're a little funky, so pretty wild if you want to compare those with these. Just the different angular momentum probabilities of where that electron is going to be. If you remember, there's going to be 2 electrons per orbital. So those are our f orbitals. And then our corresponding n to our L numbers, quantum numbers. So what is our n? Let's give a little test. What is our n number? What is that called? We go back. That is going to be a little too far back. First principal quantum number. And then the second quantum number is going to be our angular momentum number. So first quantum number is n. It's principal quantum number. And then the second one is angular. You can think about angular as the shapes or what they specifically look like. And then here's f orbitals again. And I think it's interesting to note that the periodic table really tells you a lot about these orbitals, and that these s, p, d, and f blocks are the corresponding orbitals, or the shapes. So the s, we have the circular ones, and the p, we've got the figure 8 kind of looking orbitals, the d, the clover, and then the f, the super weird ones, like over here. So I think it's super interesting if you're ever looking at element, you can kind of see what kind of orbital that element would have based on the periodic table, which is super fascinating. So let's talk about the S sublevel. So our N level is going to be, if we go back, that's our first energy level. The first energy levels. Instead of, now we're getting into the sublevels of that. So let's go back. S corresponds to your sublevel. So we have S going to be S, P, D, or F. 0 is S, 1 is P, 2 is D, and 3 is F. So these are basically what we talked about with L. It's just another way to describe. So this is your subshell, whereas N is our actual shell. Subshells, and then these correspond directly to your L number, basically just a code for your L number. So the number of sublevels is always going to be equal to the N value, which is important to know. So like if we have N equals 1, we'll have 1 sublevel. If we have N equals 2, we'll have 2 sublevels, and so forth. So let's do a little practice question. What is the name of the subshell N equals 3 and L equals 1? So just think about that for a minute. So the answer is going to be 3p because N equals 3. And so that's just easy. We're going to carry that 3 over. And then L, if we remember, when L equals 1, that's going to be our P. So that's just something, just SP, D, and F, if you remember. So L equals 1, that's P. If it was L equals 0, then that would be S. So then we move on to the magnetic quantum number. And what the magnetic quantum number tells us the specific orientation of the orbital. So if we look at this, we've got S, which has a straightforward orientation because if you just spin a sphere, it's just going to be the same orientation. So we only have one orbital then. But for the p orbitals, we will have 3 different orientations we can do on the x-axis, the z-axis, or the y-axis. And then for the d orbitals, we can flip the clover quite a few different ways along those 3 axes. And then same with the f orbitals, we can flip them. So basically, each orientation of this molecule is considered its own orbital, or its own probability of that molecule being in that rotation at that time. So the equation for this magnetic quantum number is 2L plus 1, which is why we have the little L. You can help you remember that equation from this little sub L we have on M. So if we had, so let's put this equation into context here. So with the P, our P is going to be 1, right? P is going to be 1. So if we have our P orbital here, we'll plug in the 1, 2 times 1 plus 1. So that's 3 different orbitals. Or you can just think of it as negative L2 plus L. So for our d orbitals are L is going to be 2, right? So we have -2, -1, 0, 1, and 2. And so that gives us, that gives us 5 different orbitals. 5 different orbitals here. And then for our f orbitals, we're going to have -3 to +3. So we're going to have -3, -2, -1, 0, 1, 2, and 3. So that's going to show us the number of orbitals or the number of orientations that we have. And this can show us some of the magnetic properties that it has. So, practice question. How many orbitals does the d sublevel have? And that's just going to be using what we just learned with the magnetic quantum number here. Let's look at our answers. Okay. Yes, this is not a practice question. Whoops. So, if we have our d sublevel, our L is going to equal 2. So -2 to 2. And that's going to give us our 5 separate orbitals. And each section of these is going to have its own orientation or its own orbital. So yes. So next, these are just our ML values. Next, we're going to talk about the spin quantum number, or M sub s. So the spin of the electron describes its magnetic field or energy specifically. And the spin can be up or down because we have these arrows in each atom of going up and down. And then just with all of these 4 quantum numbers, we have 4 sets of unique quantum numbers. And it's basically like an address or a specific name of describing, so you understand, like we can reference a specific orientation or know what kind of, what the molecule looks like in 3D. Or we have a probability of where that electron is going to be and what it looks like, and as well as somewhat of how it connects with, or like bonds with others. That we obviously get into that later. But because of the Pauli exclusion principle, you can put an up or down arrow. So you can only put an up and a down. And no 2 electrons in the same atom can have the same quantum number. Because if you're connecting 2 atoms and they have the same, I think the same quantum spin number is what I meant to say there. But if the same up and up, then that doesn't, that violates the Pauli exclusion principle, because you need an up and a down for it to connect. So that's important to remember here. So I thought I'd throw these charts in here. They might be useful for identifying which orbitals have the highest amount of energy. And you can also kind of do this with the periodic table. But if you remember this little chart, this shows you from top to bottom the highest energy levels per orbital. So you just go S in the first column, P and D and F, and then just number 1, 2, 3, 4, 5, 6, 7, and then you draw lines through that. And then how you read this is, let's say like 5P would be a lower energy than 6S. So we have the highest energy here, and then slowly going lower, and then you start down at the bottom here. So 7P has the highest energy level. Then it will get lower with 6D, lower with 5F, lower with 7S. So 7S is actually a lower energy level than 5F, which is interesting. And then this little chart can also help you visualize all those different quantum numbers that we talked about. So we have N, and then the type of sublevel of our S subshell, and then we can get the number of orbitals per type. This specific chart doesn't have the L number, but then to calculate the number of orbitals per level, we can do N squared, which is also helpful. And then we can also calculate the number of electrons in an energy level by 2N squared, which is also helpful. So we will have another practice question. What are the 4 quantum numbers that describe the 2p5 electron? So try to think of those for a minute. Alrighty, so for our N number, we're going to have N equals 2, or the second energy level, because we have the 2 here. And then our L is going to be 1 because it's a P. If it was an S, then it would be 0. If it was a D, then it would be 2. If it's S, then it would be 3. The M sub L is going to be 0. And the M sub S is going to be -1/2. And we're going to show you why right here. So we have L, and L is 1, so we'd have -1, 0, and 1, because our L's, we have a negative L to a positive L, and so that gives us 3 different orbitals, possible orbital orientations here. And then it's going to be a -1/2 because the last full orbital that we have, there is a down here. Or no, that's all right. So we have 5. The 2p5 has 5 of these arrows. So we go 1, 2, 3, and then 4, 5. So the last one is the one we're more concerned about, whether it's up or down, filling that set. So we know it's a -1/2. So how many electrons can be in the 4D subshell? So try to think and figure this out. I know I kind of have the answer right here, but try to figure that out on your own. Okay, so this is going to be 10, because in the D orbital we have L equals 2, and because it's a D, because of the letter, and when L equals 2, our M sub L is going to be -L to positive L, so -2, -1, 0, 1, and 2. So that's 5 orbitals, and then there's 2 electrons in each orbital, so 2 times 5 is 10 total electrons. And then I just wanted to wrap up with, you can also tell with the periodic table how many electrons you have in each orbital, from the blocks. So the S block, each column is going to be an electron. So in the S block, there's 2 electrons. In the D block, there's 10. P block, there's 6. And F block, there's quite a few. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I just thought that was kind of interesting way to tell how many electrons are in each orbital. So hopefully that helps with the quantum numbers and orbitals, and best of luck with studying.